Welcome to our number theory series. Today, we are going to explore a fascinating and foundational concept known as the greatest integer function. Imagine you are walking down a staircase, and each step represents a whole number. If you stop halfway between step 3 and step 4, gravity dictates that you must rest your feet on a solid step, so you naturally settle on step 3. This is exactly how this function works in mathematics. It takes any number, no matter how messy or fractional, and pulls it down to the nearest solid whole number below it. Let us dive in and see how this mathematical gravity operates. Now that we have our staircase analogy, let us look at the formal mathematical definition. Why does this concept matter? In mathematics, we often need a reliable bridge between the continuous world of decimals and the discrete world of integers. The greatest integer function provides exactly that. It takes any real number as its input and outputs the largest integer that is less than or equal to that input. We usually write this function by placing the number inside square brackets or special floor brackets. If the number is already an integer, the function leaves it completely alone. But if the number has a decimal part, the function moves to the left on the number line until it hits the very first integer. It is crucial to remember that it always moves to the left to a smaller value. Before we move on, let us see this downward pulling behavior with a concrete visual example. Here we have a standard number line. Look at the positive decimal 2.7. It sits between 2 and 3. The function moves our eyes to the left, chopping off the decimal part and landing exactly on 2. Now, look at the negative decimal, negative 1.3. This is where we must be very careful. It sits between negative 1 and negative 2. Moving to the left takes us to negative 2, not negative 1. This perfectly illustrates why we call it a floor function. It always pulls the value down to the next smaller integer, regardless of whether the number is positive or negative. This visual understanding leads us directly to the fundamental mathematical inequality that defines this function. Conceptually, this rule sets the strict boundaries for what the output can be, guaranteeing predictable behavior. The formula states that the output integer is always less than or equal to the original number x. Furthermore, the original number x is strictly less than the next consecutive integer, which is the output plus 1. Let us break down the symbols. The variable x represents any real number you choose. The expression in brackets represents the integer output. As the value of x increases, the output stays completely flat until x hits the next whole number. At that exact moment, the output jumps up by exactly 1. This creates a step-like pattern if we were to graph it. Now that we have our formula, let us build confidence by evaluating the greatest integer function for a few different types of numbers. We are given a positive decimal, 4.7, and a whole number, 5. Our strategy is to picture each number on a standard number line, locate its exact position, and move our eyes to the left to find the very first integer. For the positive number 4.7, we locate it between 4 and 5. The integer immediately to its left is 4. The function simply chops off the decimal part. Next, we look at the number 5. Because the formal definition says less than or equal to, the function is satisfied immediately. It leaves the integer exactly as it is. Continuing with our evaluation, we must now test a negative decimal, negative 3.2. This is where many students make a mistake, so we must be very careful. We locate negative 3.2 on the number line. It sits between negative 4 and negative 3. Remember our rule, we must move to the left. Moving to the left from negative 3.2 takes us to negative 4, not negative 3. Negative 3 is actually larger than negative 3.2, so choosing it would violate the less than or equal to rule. Physically, this means the mathematical gravity always pulls downwards, towards negative infinity. We have now successfully evaluated all three types of numbers. So we have proven that we can evaluate basic numbers. This brings us to a powerful application in number theory. The greatest integer function is not just used for rounding numbers. It is the star of a famous theorem called Legender's formula. Why does this matter? When dealing with massive numbers, like factorials, finding their prime building blocks is incredibly difficult. A factorial, written as n exclamation mark, is the product of all positive integers up to n. Legender's formula gives us a shortcut to find the highest power of a specific prime number that perfectly divides that massive factorial. It systematically counts how many times that prime number appears in the prime factorization without ever needing to calculate the massive factorial itself. Let us understand where this formula comes from conceptually. Think about the numbers from 1 to n. Some are multiples of our prime p, contributing one factor. Some are multiples of p squared, contributing a second factor, and so on. The formula adds all these extra factors together. Let us define the symbols. The variable n is the large integer for our factorial. The variable p is the prime number we are testing. The symbol k is an exponent that starts at 1 and increases towards infinity. The large sigma symbol means we add all these terms together, and the brackets represent our greatest integer function. As k increases, the denominator grows. Eventually, the fraction becomes less than 1, the greatest integer function turns it into 0, and the sum naturally stops. Now that we have used this formula conceptually, let us see it in action with a concrete example. We are asked to find the highest power of the prime number 3 that perfectly divides 50 factorial. In other words, how many times can we divide that massive product by 3 without getting a decimal remainder? We choose Legender's formula because calculating 50 factorial directly is practically impossible. We set our target number n to 50 and our prime number p to 3. We start with the first power, dividing 50 by 3. This gives 16.666 repeating. Applying the greatest integer function pulls this down to 16. Physically, this tells us there are exactly 16 multiples of 3 between 1 and 50. Continuing our calculation, we move to the second power of our prime number. We divide 50 by 3 squared, which is 9. We are looking for numbers that contain a second factor of 3. 50 divided by 9 gives 5.55 repeating. The function pulls this down to exactly 5, accounting for the extra factors provided by multiples of 9. Next, we move to the third power, dividing 50 by 3 cubed or 27. This helps us find numbers hiding a third factor of 3. 50 divided by 27 is approximately 1.85. The function strips away the decimal, leaving us with 1. This means there is only one multiple of 27 between 1 and 50. We are almost done with our calculation. We try the next power, setting up the fraction of 50 divided by 3 to the fourth power, which is 81. Since 50 is smaller than 81, the fraction is less than 1. The greatest integer function makes it 0. This is our signal that we can stop calculating. Finally, we add our individual step results together. 16 plus 5 plus 1 plus 0. This gives us a total of 22. Physically, this final answer means that 3 to the power of 22 perfectly divides 50 factorial, but 3 to the power of 23 would leave a remainder. We have successfully broken down a massive factorial. Now that we have used this formula to solve a complex problem, let us look at why this matters in the real world. The greatest integer function is incredibly important across many fields beyond pure mathematics. In computer programming, it is used constantly. When a program calculates a position, it often gets a floating point decimal. But memory addresses must be exact integers. The floor function converts these decimals into valid integer indices for arrays, ensuring the program looks up the correct data. Furthermore, as we saw with Legender's formula, it is the primary tool for prime factorization of massive numbers. This ability to cleanly strip away fractional parts is a foundational step in cryptography, which is the science of keeping all our digital information and online data secure. We have covered a lot of ground today, so let us review the most important ideas. First, the greatest integer function is a reliable mathematical tool that always rounds any real number down to the nearest whole number, moving left on the number line. Second, it acts as a crucial bridge, allowing us to translate continuous decimal values into the discrete world of integers. Finally, we saw how powerful this simple downward pulling rule can be when applied to Legender's formula, unlocking the ability to find the prime factorization of enormous numbers without ever needing a calculator. You now have a solid understanding of this foundational concept in number theory. Excellent work today, and keep practicing these principles.